Right. So let us see the response of series RLC circuit, in which what we take is resistor, inductor and capacitor, three elements which are connected in series as like this. So let me take the R, and whose value is capital R, and it is connected in series with some inductor whose inductance is L, but inductive impedance is JXL in frequency domain. Similarly, so we have a capacitor whose capacitance is a C, but its impedance in AC system is minus JXC, and these three elements are connected in series as like this. And if I have some total voltage across this entire system is V bar, here to here the applied voltage is V bar. As a result of this voltage, we may have some current passing through this series circuit, and as current pass through this series circuit, then we will see some voltage across the resistor, which is, let us say, VR bar here to here, and also we may see some voltage across the inductor, which is VL bar. Everything is in phasor, try to observe. And we may see here voltage across the capacitor as VC bar. So these arrows represents that this arrowhead represents positive, non-arrowhead represents negative, as like this. In DC system, if we compare the DC with the AC, arrowhead points the positive, non-arrowhead points the negative. So this is what the series RLC circuit. Now let us assume that some voltage or current, it's your wish, there is no fixed hard rule in this, but preferably in series circuit current is common through every element, so we choose let the current I bar is equal to I at an angle of 0, I at an angle of 0. That means the current might be something like this, I of t is equal to Im cos omega t plus 0 in this form. If we convert this I of t into phasor form, what we get is I at an angle 0, where I is the RMS value of the current, which is equal to Im by root 2. Clear? This is what the current. This is our assumption that current is in this form. So if so, we determine rest of all the parameters. Let us see how we determine. So now if we know the current, then can we find voltage across this resistor by Ohm's law?
Sir.
So voltage across the resistor, which is VR phasor, is equal to current into resistance. So how much is the current is I at an angle 0, resistance is R. So simply this is equal to IR at an angle 0 degree. This is what the voltage across the resistance. Similarly, let us take the voltage across the inductor VL bar. How we find? The same current is also passing through the inductor I into its corresponding impedance. How much is the impedance of this inductor? Is ZL, which is equal to JXL. So I can write this as initially ZL, I into ZL, which is equal to I at an angle of 0, whereas ZL, so we had seen that, so ZL can be written as in polar form or rectangle form as JXL, or simply XL at an angle of 90 degrees. We seen that J is equivalent to 1 at an angle 90. So you can replace J by angle of 90 simply. Similarly, capacitive impedance ZC is equal to minus JXC, which can be written as XC at an angle of minus 90 degrees, as like this. Means these are the rectangle forms, these are the second things are the polar forms, which are having magnitude and angle. Whereas rectangle form, it look like real part and imaginary part. What is the real part in this? 0. 0 plus JXL, 0 minus JXL, like that. Okay. So now I can write ZL as because it is multiplication, preferably in multiplication use the polar form, which is XL at an angle of 90 degrees. Then in order to get these things, so you can just multiply the magnitudes and add the angles, that is I into XL at an angle of 0 plus 90 is 90 degrees. What is this? Voltage across the inductor. Now similarly, let us find voltage across the capacitor also. Vc is equal to, same current is passing through the capacitor also, I into Zc, which is equal to I at an angle of 0, Zc is Xc at an angle of minus 90, Xc at an angle of minus 90, which is equal to Ixc at an angle of minus 90. Now, by using KVL, by using KVL, by using KVL, what can we do is that the total voltage across this entire RLC combination is sum of the voltage across the resistor and voltage across the inductor and voltage across the capacitor. So, now I can write V is equal to VR bar plus VL bar plus VC bar. See that this is phasor addition. It is not simply VR magnitude, VL magnitude, VC magnitude. It is phasor additions that you should carefully observe. Everything we are writing as phasor form. So, how much is VR is IR in at an angle of 0 plus IXL at an angle of 90 plus IXC at an angle of minus 90. Now, whenever additions are there, try to express these things in rectangle form so that we can add up all real parts and all imaginary parts. Okay. So, now I will make this into some rectangle form as simply IR. IR at an angle 0 is equal to IR plus JIXL. Why? Because angle 90 degrees is equivalent to J. Just now we had seen. So, this is minus JIXC. Now, if we take the current common out of all these things, it look like I into R plus J is common for these two terms, which is imaginary. So, if I will take J common, I will get XL minus XC. XL minus XC. This is what the total voltage V. Now, try to observe this entire impedance, this entire thing I can treat as total impedance of the circuit. See that if I will consider the total impedance is sum of each of the elements impedance, that is what? Resistive impedance, inductor impedance, capacitive impedance, ZC. If I will add up all these things, how much I will get? Check it. R plus JXL minus JXC. Now, if I will take common this J, what I will get is J into this is L XL, XL minus XC. Now, try to observe it is in the form of A plus JB form, that is rectangle form. So, can I convert this into polar form as like this? Magnitude of the real part, which is R square, plus magnitude of the imaginary part XL minus XC whole square. This is what the magnitude. How much is the angle? Angle is tan inverse of
Tan inverse of minus B by A.
B by A, which is XL minus XC by R. So, XL minus XC, real imaginary part divided by real part. If imaginary part is negative, then we take negative also. Okay. Now, this entire thing, instead of writing every time this much big expressions, what I will say is that this is the magnitude of ZT. Magnitude of ZT I will represent as mod ZT. The angle I will represent as theta. Where let me write mod ZT is magnitude which is equal to square root of R square plus XL minus XC square, where theta is the angle which is equal to tan inverse of XL minus XC by R. Now I can put this R plus J XL minus XC as ZT, this entire thing as ZT, but ZT can be written as mod ZT at an angle theta. So I'll write this as I mod ZT at an angle of theta. So this is what the total voltage across entire RLC combination. Entire RLC combination. Now if you want, just you can even go with the phasor diagram. Just I will show quickly that. So we have current. So current is some angle. Let us say current is at an angle of 0 that we had seen, 0 degree, whose length is I. See this, how much is the current? Current is I at an angle 0. That means length of this phasor is I, angle of this phasor is 0. So 0 degree is, this is what the reference. If I will consider this is 0 degree, so this current should lie along this 0 line. Now I into R at an angle 0 is what the VR. So now VR angle is also 0, so it should lie on the same line, but it may have more length than the current. This green color is what the VR magnitude. How much is the VR magnitude? I into R. What is its angle? 0. That's why it is lying on the 0 axis. Next is, so our inductor voltage. See that? How much is the inductor voltage angle? Plus 90. So plus 90 is in anti-clockwise direction angles are referred as positive angles. So here I will try to draw some VL magnitude whose angle is 90 degrees. Whose angle is 90 degrees. Similarly, I will try to put up the capacitor voltage also here, but whose angle is minus 90. Minus 90 means in clockwise. So here I will try to put up the capacitor voltage Vc bar magnitude, but this is in clockwise at 90 degrees. So this is the phasor diagram of this series RLC circuit. And now if we make one more step ahead out of this, just this phasor diagram, so we can make some more interesting thing, that try to observe. When we add up all the voltages, that is resistor voltage, inductor voltage and capacitor voltage, if inductor voltage is at 90, capacitor voltage is at minus 90. So how much is the total difference from here to here? Is 180 degrees. One is at minus 90, another is at plus 90. Thereby the difference between them is 180. See this, VL is upward, VC is downward. Now for example, if something is given that VL is more than VC, if somebody told you that VL is having more value than VC, just for this case, just I want to show the phasor diagram, and let me wind up this. So I have already VR magnitude, and now VL is on the top side, VC is on the bottom side. So VL is more value, so that VL I am trying to put on the tip of VR. This is what the VL magnitude, and VC magnitude is downward, but it is lesser value. Now see that this is VR and this is VL, this is VC. Now as a result, when I add up VL and VC, what happens is that, let me take one more step beside this. See that, so if I will add up this VC which is negative to this VL, then left out thing is the difference of these two. Then how much is left out thing is, if I will deduct this amount of the green color length, then that left out whatever it is there, which is equal to this much, is what VL minus VC magnitudes. Red color one is the difference, VL minus VC. Now VR plus VL minus VC is what? The final total voltage across the RLC circuit. This is what the V. And V is making an angle of theta. See here, V has an angle of theta, positive theta. So this angle made by this is what? The theta. So in this way we can make the phasor diagram when VL is greater than VC condition. If it is some other condition, you can interpret how it look like. Just let me show that also. 1 second. If VL is less than VC magnitude, I am talking about only magnitudes. So how does it look like is that here is our VR, no change in the VR magnitude, but VL is now lesser value and VC is more value, as like this. This is what VC, this is what the VL. Then difference between VL and VC, how we get is that just subtract this amount of the VL from the VC, you subtract this amount of, you decrease the VC by this value, and the left out value is what? The left out value is what? The difference, which is indicated here with the red color, which is VC minus VL. As because VC is more, so I am taking VC minus VL. Previously VL is more, so I am taking VL minus VC. Clear? So next is the VR plus VC plus VL, all these additions is what? Is what? The total voltage across this RLC combination, which is equal to V bar magnitude. And here in this case we may get angle as negative, so which is equal to theta. This is for the case VC is more than the VL. Like this we can take up different cases. So anyhow, so this is one of the important concept, that phasor diagram of RLC circuit for these two cases. Okay, how I drawn all these things is based on these expressions only. See that VR is 0 angle, VL is 90 degrees, VC is minus 90, etc. like that. And just let me give you one more point, that just try to observe here the impedance of this RLC circuit is R plus J XL minus XC, which can be expressed in polar form as mod ZT at an angle of theta, where this impedance angle, let me write here, this impedance has some angle. How much is that angle? Is theta, is referred as power factor angle. Power factor angle. Impedance angle can also be referred as power factor angle. And generally we come across this term, that power factor. So let me define the power factor also here. The power factor is usually represented as PF, which is the cos of this impedance angle, or in simple form we can also write cos of the angle of the voltage minus angle of the current. Angle of the voltage minus angle of the current. That is what the power factor. Usually this impedance angle is the angle between voltage and current. You can see this. The current is there here somewhere, as in the first diagram. Check it here. Let me show this. See here. Here is the current. So voltage across the resistor and current both are same. So I can say The angle between current and voltage is what? Theta. So indirectly we can say the power factor angle is what? The angle difference between voltage and current. Okay. So with this, now let me take one problem and let us see one important this concept through this problem also. So a series RLC circuit is connected to a 230 volts 50 hertz single phase supply. See here, what is given is voltage is given for us. Voltage is given for us. Remember carefully that whenever voltage is given, the given voltage is treated as a RMS value. Remember this point. They will not specifically give you as RMS value of the voltage is this, and treat that this is the magnitude of the given voltage. So this is what the total voltage across this RLC circuit. If we see this RLC circuit previously, this is what the RLC circuit. This entire RLC circuit is connected across this voltage. Let me take the copy of this again. See here. So whenever you see this circuit kind of problems, so try to draw the circuit so that it gives the better understanding how to solve the problem. Now what is given is that voltage is given, which is connected across this entire RLC circuit. Now so let me write that given thing as V bar is equal to, it has magnitude and angle. How much is the magnitude? 230 volts. Then angle, if it is not given anything, you choose as 0 degree. So this is the standard procedure that if current is given, we take current itself as a reference. If voltage is given, we can take voltage itself as a reference. Nothing wrong in it. Okay. Previously, I assumed current as a reference, then I try to calculate remaining all parameters, that is VR, VL, VC and total voltage V. If voltage is given, then you can calculate all current through the branch and voltage across each of the branches. So it's not a big issue that which is reference. Okay. So here as because voltage is given, so I am considering voltage itself as a reference, which is having angle of 0. Now, so next what we need to see is that the values of R, L, C is given, but in generally in frequency domain, especially whenever you see this term, see here this term 50 hertz. Observe that this is AC system. It is AC system. So in AC, we should definitely calculate the impedances of each element. Okay. So how we calculate the impedance is that inductive impedance ZL is equal to JXL, where XL is referred as the inductive reactance, which is equal to omega L. So instead of directly like this, let me calculate the XL first, then later I will substitute there. XL is what? The inductive reactance, which is equal to omega L, where omega can be written as 2 pi f into L. Then how much is this? 2 pi f is 50 hertz and L is, how much is the L value? 13 millihenry. Milli means 10 power minus 3. So you simplify this and give me the value. So how much we will get this value is, so let me calculate. 2 pi into 50 into 13 into 10 power minus 3. So this is 4.084 ohms. This is what? Inductive reactance. Similarly, we will have capacitive impedance, which is equal to minus jXC, where Xc is referred as capacitive reactance, which is equal to 1 by omega C, which is equal to, omega means 2 pi f. So C is already there, so C. Now substitute these values. 1 by 2 pi into 50 into C is, so how much is the C value? So 140 microfarad. So 140 micro means into 10 power minus 6. So let us calculate this value also. 1 divided by 2 pi into 50 into 140 into 10 power minus 6. So how much I got is that
22.73.
22.736 ohms. Right, very good. Now I got the total reactance of these circuits. See that inductive reactance is XL and capacitive reactance is XC. Now in the total impedance of the circuit ZT, try to see how I will get is first element is resistor, so its impedance also resistance. Second element is inductor, so its impedance is ZL. Third element is capacitor, so its impedance is ZC. Now if I will put all these things together, what I will get is that JXL minus JXC. Now if I will simplify this entire total impedance as substituting all these values, R is 5, so 5 plus J into J I can take common, so how much is the XL? XL is 4.084. How much is the XC? 22.736. So XL minus XC. So then if I'll simplify this, XC is more, so I'll be getting this as minus. So how much I'll get? 22 point this minus
Minus
4.084.
18.652.
Okay, very good. So minus 18.652 J. Now try to see in this impedance what is the real part. Real part value is minus 18.652. This real part is generally referred as total reactance offered by this circuit. This series RLC circuit has two reactive elements. One is offering XL, another is offering minus XC. So total together is when you combined this total impedance, the imaginary part in the total impedance is referred as the total reactance. Total reactance. Total reactance is equal to 18 point. Of course, it is negative, but so it is capacitive in nature. If it is negative, so I can say value is 18.652 ohms. This is what the first bit. And second one is total impedance. The impedance is already calculated. So the total impedance or simply impedance, the impedance is ZT, which is equal to 5 minus 18.652, but preferably express this in polar form. Just convert this into polar form. This is in rectangle form. So now let me put this into polar form. 652. How much I will get is 19 point, magnitude is 19.31, angle is minus 74.99 degrees. So next what else is there? The current drawn. So how much is the current? That can be obtained, the current, as simply like this. I bar is equal to the total voltage divided by the total impedance ZT. As like this, see here, I need the current voltage divided by total circuit impedance, which is ZT. This entire thing we obtain as ZT. So if I want I and V relationship, I can directly write V by I is equal to ZT or I is equal to V by ZT. So that what we are doing. So how much is V? Is 230 at an angle 0, and ZT can be written either in rectangle form or polar form, but here it is division. So if I will write in polar form, it is much more helpful. So 19.31 at an angle of minus 74.99. So this value is, how much is this? Check it. So 230 divided by the answer which I already did. So this is 11.91.
11.91, sir.
Yeah, very good. So at an angle of
74.99.
74.99. Very good. So this is what the current. But if I need only current magnitude, so I can say mod of this which is equal to magnitude of this. How much is that value? So magnitude of this is what? This much. So which I can say 11.91 amperes. Nothing wrong in expressing polar form as magnitude and angle. But if somebody asks only current, that only express the current magnitude value. So which is equal to 11.91. Then the final one is the power factor PF. So PF is the cos of the angle between voltage and current. If you know voltage and current both, directly you can do like that, or if you already know the impedance angle, directly put that angle. We already calculated impedance. See, angle is already known. How much is the angle? 74
minus
point this.
74.9.
So now we can put that thing over here, cos of minus 74.99, but whether it is minus or plus, it doesn't matter. This negativeness is expressed, I will tell you. So first find this value, cos of 74.99. So how much is this? 0.258. So see this, as because here try to observe, XL is 4.084, XC is 22.736. So if we observe carefully, XC is more than XL, and that means if Xc is more, means capacitance nature is dominating. So we already seen previously, in case of capacitors, the current leads the voltage. Current leads the voltage in case of capacitor. This you should remember, these points, important points. If it is the inductor, current lags the voltage. Okay. If inductor is dominating, then current lags the voltage. So that negativeness here, whatever negative is there, this negative factor, that will be named here as leading, as because it is capacitive nature. Okay, just we will not say there is a difference between like cos of plus 74 or minus 74, but that negativeness is said as leading nature. So in this way we can do the power factor calculations.